In this lab today we're going to create a beat frequency, but we're going to do this in a unique way. We're going to apply our two different frequencies across a nonlinear medium, namely across an argon gas. The frequencies are going to be of sufficient power as to ignite the gas into a plasma, and we predict that the plasma shall emit a beat frequency. This is our plasma bulb. It has an electrode on each side, the left electrode and the right electrode. And to the electrodes are connected the leads, which extend to the amplifier. So the amplifier is going to apply a dual frequency signal across the argon plasma and ignite it. This is what the diagram of the lab experiment looks like. We have an audio amplifier on this side. It's an incredibly highly powerful audio amplifier. It's going to output a frequency 1 and a frequency 2. This is a dual-sided amplifier. The frequency 1 is slightly offsetted from frequency 2. And it's going to extend across 11 feet of lead wire to the argon-filled gas bulb. This is called an argon phanatron. And the power put across the electrodes will ignite the argon into a plasma. And since the two frequencies are slightly offsetted from each other, the offset should create a beat frequency. That's the prediction. Now, what we're going to do is, this is a depiction of the beat frequency here. We're going to place an oscilloscope with a wire loop probe out into the field where the beat frequency should be emanating from the glass bulb. And we're going to see if we can pick up a beat frequency. Also, what we can notice with this diagram is that the power coming out of the amplifier is so incredible that it's going to make the leads that are extending to the glass bulb, it's going to make them hot with signal. And what we're going to see is that these two signals radiate into the atmosphere from these leads, and they interact and create a sort of a three-dimensional beat frequency in the environment of this experiment. We're going to place a sensor in the middle of the two leads about 10 foot away from the phanatron, just to see if what I'm saying is correct. If the leads are emanating their frequencies way back here near the amplifier, and they're creating a beat just in the air across the two leads themselves before they even get to the phanatron tube. And we're going to place an oscilloscope there in the lead wire field. That would be close to the amplifier, just to see if we're picking up a beat frequency way back there. The idea of this experiment is that the beat frequency is three-dimensional in the room. So this is called the three-dimensional beat wave lab. And here's the setup. We're going back to our argon-filled glass bulb. You'll see there's a lead connected to each end of the bulb. The leads extend 10 to 11 feet back to the audio amplifier. This is a vacuum tube audio amplifier, and it's powered at over 700 volts DC. So we're gonna oscillate this 700 volts DC at an audio rate, and we're gonna light up the plasma at that audio rate. Let's take a look at our frequencies here, just for reference. Our target frequency is 196,000 hertz. Being an audio amplifier, we're not capable of generating that. So we're going to go downwards in frequency and create a sub-multiple of that, which is 1400 hertz. So our target is a 1400 hertz beat. And in order to accomplish that, to each electrode, we're going to supply higher frequency beats. To electrode 1, we're going to apply frequency 1 of 1400 hertz. And to the second electrode, we're going to apply a frequency of 15,400 hertz. Both of these frequencies are related in that they are higher multiples of 1400 hertz. The frequency 1 is 1400 hertz times 10, and frequency 2 is 1400 hertz times 11. And so we have a minus frequency of 1400 hertz itself. And if you take all three frequencies, 14,000 hertz, 15,400 hertz, and 1400 hertz, you get a total harmonic relationship between the three. So let's turn on our amp right now. I'm going to move over to the amp. We have our power supply turned on, which is reading out on the meter at 750 volts. We have our oscillators also turned on, and we're using a Feltec generator to create the frequencies. I'm going to hold the camera still. We can see that channel 1 is a sine wave on, set at 14 kilohertz. Channel 2 is a sine wave on, set at 15 kilohertz and 400 hertz. They're both having a duty cycle of 50%. Now I'm going to actually turn the amplifier on right now. You can see the vacuum tubes light up. We come back over to the Fanatron bulb, and we can see that it is lit and glowing blue. Now we're back at the amplifier again, and we have a test. We have a test lossy dielectric here. It is an apple with two nails drove into it, and we place the scope probe across it for sensing the signal that's through the apple. This apple is placed in the middle of the two leads, far away from the Fanatron, actually 10 feet farther from the Fanatron. And if we look at the signal we're getting, we're actually seeing a beat. That is a 1400 hertz beat right there. Now if we move across the room, we can see that the Fanatron is lit. We're going to move past the Fanatron. Now we're in airspace that is beyond the Fanatron and beyond the leads. And there is an oscilloscope placed over here, and it has a loop, a wire loop connected to it. So we're going to bring the wire loop into the airspace beyond the Fanatron and take a look at the oscilloscope.